Hello everyone and welcome to the Arup set. We are at the Batimat construction exhibition and today we are going to talk about the evidence for the fire safety design of open plan spaces with timber. So we have people here who research on the timber building in fire. Dr. Panos Kotsovinos, hello.
Nice to meet you.
So you are senior fire engineer and with you Dr. Eirik Christensen, hello.
Hello.
So you are an engineer from Arup, UK, who have been involved in multiple large-scale fire experiments with and without exposed timber. And with us also Dr. Mohammad Heidari. Hello.
Hello.
So you are a fire safety engineer. So great to have you here. Can you tell us more about this large-scale experiments?
Of course, Liam. To give you a little bit of context, we have a lot of clients and architects that we work with that they are interested in designing buildings that are that have mass timber as their primary construction element, and that is cross-laminated timber and glue lam that are the most typical materials used for this type of applications. These type of materials are going to be used because of their reduced carbon residentials, but also because of the efficiency that can be led in design and in speed. Now, when using these materials, particularly for high-rise buildings and high-risk applications, we also have to consider fire safety. As timber is a combustible material, it can add to the fuel of the fire, which could increase the fire severity inside the compartment and outside the compartment. So as Arup, working with Sécurité and Imperial College, we carried out 4 experiments last year. These experiments, they are quite large scale and they consider different parameters such as ventilation and the surface of the exposed timber as well as the water mist system. In the slides on the background, you can see the facility. It's a 350 meter squared facility with a timber ceiling and multiple openings. And in the first experiment, we just considered the inclusion of a timber ceiling and how that affects the fire dynamics, smoldering and charring of the building. In the second experiment, we reduced the ventilation by half. In the third experiment, we looked at water mist as a practical mitigation measure. And at the fourth experiment, we encapsulated 50% of the ceiling.
Okay.
Panos, can I ask you a question, any of you? Why do you need to do that at that scale? I understand it was the largest experiment ever done in timber.
Yeah, it's a really good question. So since around the year 2000, there's been over 60 experiments that have been conducted, specifically trying to answer this question of what is the impact of exposed timber on fire dynamics. And while these have been incredibly valuable in terms of the data and information we've received from them, they're limited in their scale. So because these experiments have typically been limited to around 90 meters squared, there's a lot of uncertainty in how these results extrapolate onto larger scale buildings. 90 square meters is more commensurate to maybe a residential unit or a smaller office space where you might have 8 or 9 people working. But modern office buildings today are over 1,000 meters squared. So there's uncertainty in how well it scales up to something at that size. So we were particularly interested in conducting an experiment closer to the real scale, where you can start studying some of the more complex fire dynamics relating to the spatial distribution of the fire dynamics, as well as understanding the spread of the fire within the compartments. And so it really did push us to look at experiments that weren't just typical, let's say less than 90 meters squared, but up towards what we did, which was 350 meters squared.
Okay. Can you tell us about the process from conducting these experiments?
First of all, given the importance of this work for Arup and for the work we do, we had to select the right partner. We were looking for a fire testing laboratory that has the adequate experience of undertaking such a unique large-scale experiment with quality and above all safety. As a result, at the inception of the project, we got in touch with quite a big number of fire testing centers, and we asked them to provide some support for us. And after a competitive bidding process that was managed by an external project manager, SERIB was selected as the fire testing center to work on this project. SERIB has a lot of experience in undertaking large-scale experiments of this kind with external partners as well, including Arup and our collaborator Imperial College London, as part of previous experiments that we undertook in Poland. And they also have a unique test facility where the building that we showed earlier can be built from scratch. The building that we see was designed by Arup, but its actual design is based on a previous experiment that was undertaken by Imperial College, where Arup and SERIB were collaborators, and was built at a service facility at Epernon. The facility was provided with extensive instrumentation, including thermocouples and plate thermometers, to measure the fire dynamics within the compartment. We had cameras to look at the movement of the fire, thermocouples within the timber members, and thermocouples and heat fluxes outside the compartment, so that we can look at external flaming and external fire spread to adjacent properties. One thing I would like to note is the fact that all these 4 experiments were undertaken in 2021 during the pandemic, actually in the heart of the pandemic, where we were not allowed to travel internationally, and they were conducted under difficult situations. Despite this, we had a lot of interaction with all the collaborators, that was SERIB and Imperial College, and we worked very well together as a team. And I would like to thank everybody for being able to deliver this in such a difficult times, and being able to work on the goals and of the project.
Yes, I can imagine. How did these experiments go? Can you tell us what did you discover and observed?
Yeah, absolutely. So the experiments went incredibly well. We obviously, as Panos said, had instrumented the compartment quite extensively, and so gained a lot of data, and from that a lot of insights about the compartment. Firstly, fortunately, the experiment confirmed a lot of the knowledge that had been presented already in previous research. For example, vertical elements experience much more severe thermal exposure in compartments with timber ceilings. You also have a longer or prolonged decay period because of this timber ceiling. And interestingly, that the CLT, when it's isolated, tends to burn out at a very similar time to the fuel load along the ground, kind of suggesting that an isolated timber element requires some external energy, particularly the ceiling, to sustain its burning, which is useful in design concepts, as the fuel loads can be linked to a certain extent. But perhaps maybe more interestingly is the new information and the new knowledge that we gain from these experiments, given their size and scale. Maybe first of which is related to this image that we see above. The big risk that we identified is the rate at which the fire spread, particularly across the ceiling. So as you can see, once the CLT ignited on the ceiling, the fire spread incredibly rapidly across the ceiling, driving the spread also along the fuel. So as you can see in this image, the ceiling is alight, but the fuel on the ground has yet to start spreading. But because of the re-radiation between the ceiling and the fuel, this really increased the rate at which the fire grew. Something that wasn't expected, or at least hasn't been observed before in research. And because of the contribution of the heat release, as you can see here, to the overall fire, the total and the peak heat release rate from these compartments is greater than what you would expect in non-combustible compartments. And as a consequence of that, we also saw much greater external flaming, where not only the flame heights were larger in height, but also the thermal severity of the fires onto the facade or even the buildings adjacent was much greater. All of these things need to be considered in design. Unique to these experiments as well is after the end of flaming, we continue to observe the compartments for several days afterwards to study smoldering in particular as a risk that we had identified as lacking within the research. And what we'd observed was in several locations and in all the experiments, smoldering did continue to propagate for several days, and in many locations even spread through the thickness of the CLT, which was 160 millimeters. And that clearly has quite significant design implications on the structural capacity, and not only just structural implications, but also for the fire strategy itself. In Code Red 2, as Panos mentioned, we changed the ventilation and studied the impact that had on the fire dynamics, a particularly relevant metric given the uncertainty around glass breakage during fire events, and found that both the duration of the fire but also the external flaming was much greater due to this reduced ventilation. In Code Red 3, we implemented a water mist system to test its efficacy, and found that when installed correctly and designed correctly, it does seem to be capable of preventing the ignition of the CLT. And then finally in Code Red 4, we encapsulated half of the exposed CLT and found a decrease in both fire size, flame height, and overall duration of the fire, suggesting that encapsulation does have some benefits to the fire strategy. Yeah.
Yeah, I was lucky to be there, and it was impressive. That brings this question to my mind that actually running these experiments or doing these experiments show how Arup is in forefront of the design of timber or fire safety design of timber buildings. How does Arup apply this?
Yeah, as you know, Mohammed, we have a lot of data to consider and go through, like you produced them for us. So the analysis is still ongoing, but the results that we already have from our work and the future analysis goes into developing new design methods that we can use for the fire safe design of mass timber buildings, and they are already making their way through in current projects and will also inform the design of future projects. We have also been speaking to people from the fire service, approval authorities, the insurance sector, sharing our results and trying to understand how this data could influence their work or how they can impact our work as well. And we also plan to, once the analysis is complete, to share these results with the whole world so that everybody can benefit from the information. We also hope that in the long term, this data can also help governments or other standardization bodies to improve building codes too.
And by the way, and maybe for the people who are watching us, have you published this work if people would like to read more?
Absolutely. So far we've published 2 academic papers in Fire and Materials covering the research that we've done surrounding Code Red 1, so the first experiment, as well as Code Red 2, the second. We've also published a magazine article discussing some of the findings that we had for Code Red 3 related to the sprinkler system. And then we're in the final stages of publishing, and has been accepted, publishing Code Red 4, the final of the 4 experiments. And then we're hoping, obviously, to continue to publish as we dig into the data and start doing more comparisons. Because from our perspective and from Arup's point of view, it's incredibly important that this information is disseminated quite broadly so that we can kind of raise the level of the construction industry and the understanding of how timber compartments behave or how fire in timber compartments behave, and ultimately try to deliver a resilient and safe and ultimately sustainable construction industry.
We are almost at the end of this interview. let's talk about the future. What is next?
So linking to, I think, Erik's last sentence there, we are still doing an ongoing analysis of the data, and we hope that soon we will be able to publish additional papers from our work that dive into the detail of the results that we had from these large-scale code red experiments, and hopefully these publications can help designers to design safer buildings, timber buildings in case of fire. At the same time, while we do this work, we have also recognized that there is an opportunity to explore the option of using hybrid timber buildings in the construction industry, and therefore we are looking to develop design methodologies involving hybrid buildings and undertake some experimental testing and analysis. And in this area, we will hope to continue to work with our collaborators at Sécurité and at the Imperial College to develop new practical solutions on the subject.
Panos, Eirik, and Mohammad, thank you very much for this interview. We can see how this solution from Arup is really helpful for the fire safety. Thank you very much.
Thank you.
Thanks, Liam, and thanks to Sécurité for their support.
Good to have you here. Thanks, guys.
Cheers.